In the vast silence of space, new dangers rarely announce themselves. Most arrive quietly. A faint light in a telescope, a name on a data sheet, a blip among billions of stars. Yet sometimes, one of those specks carries a story powerful enough to change how we see the universe itself. Astronomers working with the Asteroid Terrestrial Impact Last Alert System, or ATLAS, noticed just such a flicker in the summer of 2025. At first it seemed like another routine find, a dim point of light near the constellation Sculptor, moving slightly too fast for comfort. But its motion told a stranger tale. The object was not bound to the sun at all. Its path curved on a hyperbolic trajectory, a route that only a true interstellar visitor could follow. They named it 3I Atlas, the third confirmed object ever recorded from beyond our solar system. Before it, only Oumuamua in 2017 and 2I Borisov in 2019 had crossed our neighborhood from the galaxy at large. Both had forced scientists to question what kinds of bodies wander between stars. This newcomer promised to raise even deeper questions, and possibly darker ones. Early estimates suggested it measured several hundred meters across, traveling at nearly 61 kilometers per second, fast enough to cross the distance between Earth and the Moon in just over an hour. That velocity placed it beyond the gravitational grip of any planet or star nearby. Whatever its origin, it was coming from far away, and it would not stay long. To the public, it sounded like another fascinating headline. To researchers, it felt like déjà vu. Another mysterious interstellar body, another puzzle, another test of our readiness to face the unknown. But as the weeks passed, new data hinted that this visitor was no ordinary piece of ice and dust. It glowed too brightly for its size, emitted gases unlike any typical comet, and displayed a forward-facing tail, something the laws of simple physics could not easily explain. If the previous interstellar objects had challenged science, this one unsettled it. It was not just an object passing through. It was a messenger, and perhaps a warning from the deep galactic past. Long before the sun existed, long before any trace of Earth cooled into solid rock, the Milky Way was already shaping its first generation of heavy stars. These giants burned fast, died violently, and left behind the debris that would seed future worlds. In that violent dawn of our galaxy, roughly 10 to 12 billion years ago, a second, thicker layer of the Milky Way took form, what astronomers today call the galactic thick disk. Unlike the thin, orderly spiral where our sun resides, the thick disk is a rugged province of ancient matter. Its stars carry lower metallicity, meaning they contain fewer elements heavier than helium. That chemical fingerprint tells us they were born when the cosmos itself was still young, when only a few stellar generations had lived and died. Each collision, each supernova, sent clouds of gas and fragments into motion, some merging into new suns, others flung outward into deep interstellar space. Somewhere within that maelstrom, an icy fragment may have taken shape, a body made of primitive dust, frozen gases, and the minerals of the early galaxy. If 3I Atlas truly came from that ancient population, it would be older than Earth by at least 5 billion years. That is a timescale so vast that entire civilizations could rise and fall while it drifted between the stars. Interstellar space is not empty. It is a thin sea of charged particles, magnetic fields, and occasional shocks from distant supernovae. Any object crossing it endures temperatures barely above absolute zero and radiation that erodes its surface grain by grain. Most such wanderers would slowly disintegrate or become dark, invisible rocks. Yet the brightness of 3I Atlas suggested otherwise. It was unusually reflective, as if its crust had been glazed by countless impacts or covered in metallic compounds forged under intense cosmic rays. NASA's galactic archaeology models indicate that materials expelled from the thick disk can travel tens of thousands of light-years before being captured again by another stellar system. In that context, the interstellar visitors we have seen, Oumuamua, Borisov, and now Atlas, may simply be the first detectable examples of a vast unseen population drifting through the galaxy. Each could represent a time capsule preserving the chemistry of the early Milky Way. When spectrographs first analyzed 3I Atlas, astronomers detected traces of carbon-rich ices and silicates that do not match the ratios found in ordinary comets. Some speculated it might have formed near the core of a supernova remnant, where extreme radiation can forge exotic molecules. Others proposed that it was a shard from a disintegrated planet, ejected during the chaotic birth of a binary star system billions of years ago. Either way, its journey was unimaginable. To reach our solar system, it must have wandered for millions upon millions of years across interstellar distances. Perhaps it passed within sight of other suns, grazing the edges of alien planetary systems, gathering scars and residues from every encounter. Its speed, 61 kilometers per second relative to the Sun, hints that gravity from one of those stars may have given it a final push, setting it on the course that brought it here. Now, as it approaches our neighborhood, we are witnessing the end of a voyage that began near the dawn of the galaxy. Every observation we take, every spectral line recorded, is a message from that distant past. And if our models are correct, this object is not unique. There could be billions more like it, traveling silently through the darkness, older than any world we know, older than life itself. The thought is humbling. When we look at 3I Atlas, we are not just studying a visitor from another system. We are confronting the raw material of cosmic history. It reminds us that the story of the Milky Way is still unfolding, and that sometimes the oldest messengers arrive uninvited, bearing secrets from a time when our own sun was still only a dream. On the windswept summit of Mauna Loa, one of Hawaii's tallest volcanoes, two small domes scan the night sky. Each holds a 0.5-meter telescope, part of the Asteroid Terrestrial Impact Last Alert System, better known as ATLAS. Its mission is simple yet vital: to detect anything moving fast enough and close enough to pose a risk to Earth. ATLAS takes repeated wide-field images of the sky, comparing each frame to the one before. When a pixel of light changes position, the software marks it, and within seconds a new object is logged, measured, and sent to human astronomers for confirmation. In late July 2025, those telescopes noticed something subtle. A dim streak appeared in the constellation Sculptor, moving slightly faster than the background stars. At first, it looked like any of the hundreds of near-Earth asteroids Atlas tracks every month, but after several nights of observation, its path refused to fit. The computer predicted a loop that didn't close, the hallmark of a body not gravitationally bound to the Sun. That single mathematical curve changed everything. When orbital analysts plotted the trajectory, it was clearly hyperbolic, meaning the object came from beyond the solar system and would never return. Within 24 hours, observatories across the world began to take notice. The Minor Planet Center in Cambridge, Massachusetts, verified the orbit and assigned a preliminary designation, C2025A3, Atlas. Later, once interstellar origin was confirmed, it received its final name, 3I Atlas, the third known interstellar object. The first two, Y Oumuamua and 2I Borisov, had already changed astronomy forever. Oumuamua, discovered in 2017 by the Pan-STARRS telescope, was shaped like no comet or asteroid ever seen, long, thin, and tumbling. Borisov, found 2 years later by an amateur astronomer in Crimea, looked more conventional but was chemically distinct, containing unusually high levels of carbon monoxide. Both had hinted that the space between stars might be filled with more wandering debris than anyone expected. So when 3I Atlas appeared, astronomers prepared for a scientific feast. Dozens of telescopes were tasked to follow it. The European Southern Observatory's VLT in Chile, the Subaru Telescope in Hawaii, NASA's Infrared Telescope Facility, and smaller instruments from Italy, Spain, South Africa, and Australia. Each night, data streamed in. Brightness curves, spectra, polarimetric readings. Each confirmed the same strange truth. This visitor was moving faster and glowing brighter than anything its size should. Atlas measured its brightness at magnitude 18.9 when discovered. Faint, but visible to modest professional telescopes. Its light grew quickly as it drew closer to the inner solar system. Based on its apparent magnitude and distance, early estimates placed its nucleus between 400 and 800 meters in diameter. That made it larger than Oumuamua, but smaller than Borisov. Its color was unusually neutral, neither the reddish hue of most comets nor the deep gray of rocky asteroids. Instead, it reflected light in a way that suggested a metallic or silicate-rich surface. The object's motion puzzled everyone. It was approaching the Sun at a steep inclination of nearly 125 degrees, almost perpendicular to the plane of the planets. That meant it wasn't just passing through. It was cutting across the solar system like a knife through fabric. Its incoming velocity was around 61 kilometers per second, and even after subtracting the Sun's gravitational influence, its excess velocity, the speed it would have in interstellar space, was about 26 kilometers per second. That value placed it among the fastest natural objects ever recorded. NASA's Center for Near-Earth Object Studies, CNEOS, confirmed that at its closest approach, Atlas would pass well beyond Earth's orbit. No direct threat. But scientists knew the true importance wasn't proximity, it was information. Every interstellar object carries chemical and physical data from another solar system, a snapshot of a distant world's composition frozen in ice and dust. As data accumulated, a team at the University of Arizona's Lunar and Planetary Laboratory noted something peculiar. The object's tail, its coma and dust plume, appeared to point ahead of its motion, not behind. That contradicted every standard model of cometary behavior, where solar radiation and wind pushed debris backward. At first, researchers suspected a processing artifact or a telescope alignment issue, but multiple observatories, using different instruments, confirmed the same phenomenon. The so-called anti-tail became the central mystery of 3I Atlas. While the astronomy community debated, the public's curiosity grew. Media outlets dubbed it the alien comet, though most scientists urged caution. Even so, there was something undeniably eerie about a body entering the solar system from the galactic void, shining brighter than expected, and displaying behavior no one could explain. Within a month, 3I Atlas was being tracked almost continuously by global networks, from Hawaii to South Africa, from Chile to Spain. Each observation added to a growing database shared through the International Astronomical Union's Astrometric Data Exchange Standard, ADS. Thousands of coordinates, velocity measurements, and light curve points were plotted in real time, forming the most detailed portrait ever made of an interstellar visitor. But with every new observation came new confusion. Its spectral lines showed peaks at wavelengths associated with carbon dioxide and cyanogen, yet lacked the water signatures that define ordinary comets. That suggested a body either heavily altered by radiation or composed of exotic material, perhaps from a system whose star had very different chemistry from the Sun's. By late August, the mystery deepened further. A cluster of observatories detected sudden bursts of brightness, small outbursts, as though something beneath the surface was venting gas or even detonating. Each flare lasted only minutes, but their regularity hinted at internal structure, maybe cavities or layers collapsing under solar heating. 3I Atlas was no simple rock. It was a dynamic, volatile world on a short, fiery visit. And as the days shortened and its orbit drew it toward the Sun, astronomers began to realize that soon, perhaps within weeks, it would pass behind the solar glare, vanishing from sight during its most critical phase. The countdown had begun. To the human eye, a comet is easy to imagine. A blazing head, a sweeping tail stretching away from the Sun, like a banner driven by light itself. For centuries, this image defined how people understood these travelers of ice and rock. But what the telescopes recorded from 3I Atlas turned that image upside down. When astronomers plotted its dust plume, the structure did not trail behind the nucleus. It pointed forward, almost directly along the line of travel. It was as if the comet were pushing material ahead of itself, defying radiation pressure and solar wind. At first, this looked impossible. Physics dictated that photons and charged particles from the sun strike a comet's surface, forcing vaporized dust backward. That law had no exceptions. Until now. The first reports came from the Lowell Discovery Telescope in Arizona. Their long-exposure images, cross-checked against star fields, clearly showed a narrow stream extending several thousand kilometers ahead of the body. Within days, the European Southern Observatory's VLT confirmed the same structure using polarimetric filters. This was no photographic artifact, no alignment error. It was a real, persistent feature. Scientists began reviewing precedents. A few known solar system comets had displayed faint anti-tails before: Comet Arend-Roland in 1957, Comet C 2013 A1 Siding Spring, and more recently C 2020 F3 Neowise. In each case, the effect appeared when the viewing angle from Earth lined up with the comet's orbital plane. The thin dust sheet projected forward only because of perspective. But 3I Atlas was different. The geometry of its orbit and our viewing line ruled out projection errors. The feature remained visible from multiple vantage points, across weeks of motion. A joint team from NASA's Jet Propulsion Laboratory and the University of Bern simulated possible explanations. One model suggested that the object's rotation axis might be tilted nearly 90 degrees, so jets of gas from its surface fired sideways relative to its trajectory. If those jets released large grains, millimeters or centimeters in size, the solar wind might be too weak to push them backward. Instead, inertia could carry them forward before they slowly curved into the normal tail structure. That could create the illusion of a shield of debris at the front. Another hypothesis was far stranger. Infrared data hinted that the dust grains were unusually reflective, possibly metallic. If the surface contained nickel-iron compounds or magnetized silicates, electromagnetic forces from the solar wind could behave differently, pulling material along magnetic field lines rather than pushing it away. Such interactions had never been observed at this scale. If confirmed, 3I Atlas might become the first natural object demonstrating magnetically coupled dust emission. Still, the imagery was unsettling. The forward plume looked almost deliberate, a glowing veil stretching before the nucleus like a bow wave before a ship. Online forums and even a few popular science outlets speculated that this might not be natural at all. They imagined the possibility of an engineered shield, a way for an artificial craft to deflect micro-impacts during interstellar travel. Professional astronomers dismissed the idea publicly. Yet in private discussions, some admitted that the geometry was unlike anything they had seen. To test the physics, the Hubble Space Telescope captured a series of time-lapse images using its Wide-Field Camera 3. Across 6 days, Hubble tracked subtle changes in the plume's direction. It oscillated rhythmically, matching a rotation period of roughly 8.3 hours. That measurement aligned with photometric light curve data gathered by ground telescopes, confirming that the nucleus was spinning. Such rotation could expose active regions cyclically, causing the jets to fire in alternating directions, forward, sideways, then backward. But still, the symmetry of the plume's shape remained suspiciously stable. At the Max Planck Institute for Solar System Research, specialists in dust dynamics published a preliminary report. Their conclusion was cautious. The anti-tail could form if the object had a dense, gravitationally bound halo of large particles, released earlier in its journey and moving ahead on slightly different orbits. In essence, 3I Atlas might be flying through its own debris cloud, a self-generated bow front produced by delayed ejection. If true, the structure could extend tens of thousands of kilometers and persist for months. Whatever the explanation, one fact was clear. 3I Atlas was rewriting comet physics in real time. Every frame of data challenged existing models of radiation pressure, rotation, and particle emission. For decades, astronomers had relied on the simple principle that sunlight shapes comets like wind shapes smoke. Now they faced an object that ignored that principle entirely. As the strange forward plume continued to intensify, Another realization emerged. If this debris really was concentrated ahead of the object, then as it neared the inner solar system, it would be the first thing to encounter the sun's radiation directly, and perhaps to disintegrate violently. That meant the anti-tail was not just a curiosity, it was a warning sign. The next phase of observation would determine whether this interstellar wanderer would remain intact or whether it was about to shed its outer layers in a catastrophic burst. By early September, the forward-facing plume of 3I Atlas had become impossible to ignore. Across the global astronomy network, data logs filled with identical descriptions, an expanding arc of material preceding the nucleus, persistent even as solar wind pressure intensified. It looked unmistakably like a protective shell, moving with and around the body, as though it were wrapped in its own drifting armor. The immediate question was simple, but unsettling. Could a natural object really generate such a structure? Or was something more deliberate at work? At the European Space Agency's Near-Earth Object Coordination Center in Frascati, Italy, a working group of dynamicists began to simulate the comet's trajectory and its dust envelope. They fed in data from Atlas, Hubble, and the Solar and Heliospheric Observatory, SOHO. The model revealed that the particles forming the forward plume were unusually large, perhaps centimeter-sized grains, far heavier than typical comet dust. Radiation pressure, which normally pushes fine dust backward, would have almost no effect on such massive fragments. Instead, they would drift ahead along slightly slower orbits, forming a loose bow-shaped cluster in front of the nucleus. That explanation fit the observations, but it opened another puzzle. Why would a comet emit large particles first, before releasing the finer dust seen in later stages? Ordinary sublimation does not behave that way. It tends to begin with gas jets propelling small particles outward, not with heavy gravel moving ahead. To many researchers, the pattern looked too structured to be coincidence. One possibility was electrostatic sorting. In the vacuum of space, the sun's ultraviolet light charges the surfaces of dust grains. If 3I Atlas possessed an unusually strong local magnetic field, perhaps due to metallic inclusions within its crust, the charged particles could be organized by that field, forming ordered filaments rather than random clouds. When the comet spun, those filaments might arc forward, drawn along magnetic lines. If confirmed, this would mark the first time a magnetic self-interaction had been seen shaping a comet's debris envelope. The University of Helsinki's astrophysics department proposed a second, even bolder idea. They suggested that the forward cloud might act as a natural impact buffer. Interstellar space is full of micrometeoroids, and at speeds of 60 kilometers per second, even a grain of sand carries destructive energy. Over billions of years, an object traveling through that environment would need protection. If the outer layers of 3I Atlas had evolved to fragment and reform continuously, it could shed a veil of particles that absorb and deflect those impacts. In that sense, the so-called shield would be a natural survival mechanism, a kind of self-repairing armor formed over eons of exposure. But there was another angle, one that the public could not ignore. The structure of the forward cloud, its symmetry, and the consistency of its brightness suggested an unsettling possibility: intentional design. Not mechanical design in the human sense, but perhaps something far older, crafted by forces or intelligences we do not yet understand. The hypothesis drew immediate attention after a brief paper by a small research team from Harvard University, led by Dr. Avi Loeb, known for his earlier speculation that Oumuamua might have been an artificial probe. Loeb's argument, though controversial, rested on simple logic. If interstellar civilizations exist, their debris or technology may drift through the galaxy just as naturally as comets do. Why assume that everything we see must be geological, not technological? Applying that reasoning to 3I Atlas, Loeb's group noted its constant optical brightness despite changing distances from the sun. Such stability would be difficult to achieve for a natural body undergoing sublimation. They suggested that the forward plume could represent a form of active shielding, perhaps even a controlled reaction to solar radiation, something that managed temperature or momentum deliberately. The mainstream scientific community rejected the claim as speculative, citing insufficient data. Yet the idea lingered. Even within professional circles, some conceded that 3I Atlas was acting more like a spacecraft than a comet. It adjusted brightness irregularly, emitted gas at intervals, and maintained structural coherence longer than thermal models allowed. Meanwhile, engineers at NASA's Goddard Space Flight Center approached the question from a purely physical standpoint. Could a natural object, through repeated heating and cooling cycles, generate something functionally similar to a shield? Their computer models suggested yes. If 3I Atlas had a layered surface, an inner nucleus of frozen carbon dioxide wrapped in crusty silicates, solar heat could cause pressurized gas pockets to rupture outward, pushing chunks of crust ahead of the body. Those fragments would then orbit slightly forward, reflecting sunlight like a defensive curtain. It was not intentional design, but it could look very much like one. As the object approached 1.5 astronomical units from the Sun, the forward shield brightened dramatically. Spectral readings indicated that the dust contained not only carbon dioxide ice but also complex organics, including polycyclic aromatic hydrocarbons, molecules often found in the residue of ancient star-forming regions. These compounds absorb ultraviolet light and re-emit it as infrared, effectively diffusing heat. In other words, the cloud around 3I Atlas acted as a thermal regulator. It might not have been a technological shield, but it performed the same job. Amid the scientific debates, media speculation surged. Headlines claimed the comet was a galactic visitor under protection, and online discussions drew comparisons to fictional probes and alien artifacts. For the general public, the distinction between science and imagination blurred. For the scientists watching through their telescopes, the truth was even stranger. Nature itself might be capable of building mechanisms that imitate engineering. At the Planetary Science Institute in Tucson, researchers analyzed the timing of the comet's gas emissions. They found that the intervals between outbursts aligned closely with its rotation period of about 8.3 hours. This regularity suggested an organized internal structure, perhaps with fissures aligned along specific latitudes. Each time those cracks faced the Sun, trapped gas exploded outward, launching plumes of debris that joined the forward shell. It was almost rhythmic, a heartbeat of sublimation. If this behavior was natural, it revealed a level of self-stabilization rarely seen in small bodies. If it was artificial, it meant that the craft, or whatever it was, had maintained operational systems after millions of years of interstellar travel, a thought almost beyond comprehension. For now, astronomers leaned toward the simpler explanation. 3I Atlas was a relic of the early galaxy, hardened by cosmic radiation, venting ancient gases through deep fissures, and surrounded by a halo of particles large enough to resist sunlight. A natural phenomenon, but one with uncanny precision. As the Sun drew nearer, the shield grew brighter still, glowing with a faint bluish hue. Observers at the Las Cumbres Observatory Network, using synchronized telescopes across 5 continents, noted a constant forward shimmer, like the reflection of an invisible sail. By then, even the skeptics admitted that whatever 3I Atlas was doing it well. It was protecting itself from the Sun, but protection can only last so long. The closer it came, the faster it heated. The question was no longer how it formed the shield. It was how long the shield could survive before everything behind it disintegrated. Every orbit tells a story. In celestial mechanics, motion is memory, the echo of a past event recorded in a body's path. When astronomers plotted the course of 3I Atlas, that story revealed itself as something astonishing. Its orbit wasn't just eccentric, it was hyperbolic, meaning that the object had come from outside the Sun's gravitational dominion and would leave it forever. The mathematics were clear. Its orbital eccentricity measured roughly 1.19, well above the threshold of 1.0 that marks the transition between bound and unbound motion. This single number carried profound meaning. 3I Atlas was not a child of our solar system. It was a drifter from the stars. At its discovery, its heliocentric velocity, the speed relative to the Sun, was recorded at about 61 kilometers per second, or roughly 220,000 kilometers per hour. That's more than 170 times the speed of sound in Earth's atmosphere. If the object could be slowed to walking pace and laid across our planet's equator, it would circle the Earth in less than 7 minutes. By comparison, the first known interstellar object, Oumuamua, traveled at 26 kilometers per second relative to the Sun. The second, 2I Borisov, moved at about 32 kilometers per second. 3I Atlas, with nearly double that speed, was in a category of its own. Such velocity could not be produced by solar gravity alone. It had to be launched, or flung, from somewhere far beyond, possibly by a gravitational slingshot around a massive star, or even a supernova shockwave millions of years ago. To visualize its trajectory, astronomers used models from NASA's JPL Horizons system, which integrates data from planetary ephemerides and space missions. The result looked like a long, sharp curve slicing through the plane of the planets. The object approached from the southern galactic hemisphere, rising toward the Sun's north with an inclination of nearly 125 degrees, a steep, plunging path that crossed no known asteroid belts or cometary families. No previous orbit in the minor planet center's vast catalog looked remotely similar. This trajectory meant that 3I Atlas wasn't just another comet that had escaped the Oort cloud. The Oort cloud, a vast shell of icy debris surrounding the solar system, extends perhaps 100,000 astronomical units from the Sun. Yet even at its outer edge, the Sun's gravity still exerts a weak hold. Objects leaving the Oort cloud generally do so with eccentricities just above 1.0 and velocities under 2 kilometers per second when entering interstellar space. 3I Atlas exceeded those limits by orders of magnitude. It hadn't drifted away from our system. It had come crashing in from another. Using the data from early tracking observations, orbital engineers calculated its incoming radiant, the point in the sky from which it appeared to arrive. That direction aligned roughly with the galactic thick disk, the same ancient region described earlier, a sector filled with low metallicity stars formed during the early ages of the Milky Way. The odds were small, but not zero, that 3I Atlas had once belonged to a planetary system orbiting one of those stars, ejected during a cataclysmic event billions of years ago. Astrophysicists at Caltech ran reverse integrations, computer simulations that traced the orbit backward through galactic coordinates. Their models suggested the object had entered the solar neighborhood from about 3 parsecs away, possibly near the direction of the star HD 13974, a faint yellow dwarf. At its current speed, that distance would have taken roughly 100,000 years to cross. And before that, its trail became uncertain. Beyond a few 100,000 years, gravitational uncertainties blur all traces of origin. In interstellar space, memory fades into statistical fog. The hyperbolic path also dictated the object's fate. Once past the Sun, its velocity would increase further due to gravitational acceleration, peaking near 120 kilometers per second at perihelion, the point of closest approach. Afterward, it would slow again, but never below the escape velocity of our solar system. It would leave us forever, bound for the dark between the stars, carrying with it whatever secrets it refused to yield. This immense speed had other consequences too. At 61 kilometers per second, collisions with even microscopic dust particles generate enormous energy. A grain no larger than a pinhead could strike with the force of a rifle bullet. That realization made the earlier discovery of its protective forward shield all the more intriguing. Perhaps that cloud of debris was more than coincidence. Perhaps it was an evolutionary response to the relentless impacts of interstellar dust at relativistic speeds. The Solar and Heliospheric Observatory, stationed between Earth and the Sun, recorded subtle variations in the solar wind as 3I Atlas approached. Though too distant for direct interaction, the object's outgassing seemed to carve measurable disturbances in the local plasma flow, hinting at an extended electromagnetic field around it. Was this just the effect of charged ions escaping its surface, or could it represent something more complex? A natural magnetic cocoon shielding it during its hyperbolic plunge. At the European Southern Observatory, astronomers began to debate an unorthodox possibility: that some interstellar bodies might travel through the galaxy not as random debris, but as stable configurations of charged material, quasi-natural craft shaped by electromagnetic feedback. Such formations could endure for billions of years, propelled by radiation pressure and magnetic drift, rather than by gravity alone. Perhaps 3I Atlas was one of these strange wanderers, a self-stabilizing relic of the Milky Way's ancient past. As it drew closer to the Sun, the object's motion accelerated with almost mathematical purity. Its path through the inner system resembled the plunge of a comet, but with none of the expected perturbations from Jupiter or the other giant planets. Its orbit passed nearly 2 astronomical units below Jupiter's plane, sparing it from gravitational deflection. That allowed astronomers a rare opportunity: to watch an interstellar traveler glide through our system virtually undisturbed, a laboratory of cosmic motion. For students of celestial mechanics, 3I Atlas became a living demonstration of Newton's laws on a galactic scale. For philosophers, it was something deeper, a reminder of how small our solar system truly is. Even at tens of kilometers per second, it would take this object tens of thousands of years to reach the next star. In that time, it would pass countless unseen worlds, invisible in the interstellar dark, carrying its ancient scars with it. Yet before it vanished into the night again, it would come close enough for us to witness its full transformation, the moment when cold interstellar ice met the heat of the Sun, and velocity alone could not save it. As 3I Atlas plunged deeper into the inner solar system, something remarkable began to unfold around it, an atmosphere born from heat and speed. In the vacuum of space, there is no true air, no wind, yet even a frozen rock can breathe when sunlight awakens its surface. This faint glowing exhalation is what astronomers call a coma, the thin envelope of vapor and dust that forms when volatile ices begin to sublimate. For ordinary comets, the coma is a familiar sight. For an interstellar traveler like this, it became something else entirely, a spectacle that defied precedent. By mid-September, high-resolution telescopic images from the Very Large Telescope, VLT, in Chile, and NASA's Infrared Telescope facility in Hawaii showed that 3I Atlas was developing an unexpectedly large and asymmetric coma, already spanning more than 250,000 kilometers across, roughly twice the diameter of Jupiter. That size was extraordinary for an object less than a kilometer wide. If you stood at its nucleus and looked outward, you would see a ghostly shroud stretching beyond imagination. A sphere of vapor and dust so vast that Earth itself could fit inside it 20 times over. Spectrographs recorded the gases escaping from the core. To everyone's surprise, water vapor, usually the main component of cometary comae, was nearly absent. Instead, the readings showed dominant peaks of carbon dioxide, CO2, carbon monoxide, CO, and traces of cyanogen, CN. These findings matched the earlier pattern from 2I Borisov, but were far more extreme. Such a mixture implied that 3I Atlas had formed in an environment either far colder than our solar nebula or chemically different, possibly around a star richer in carbon and poorer in oxygen. That alone made it a treasure trove of information about alien chemistry. As it warmed, the coma began to behave strangely. Most comets form tails that stretch directly away from the Sun, driven by solar radiation pressure. 3I Atlas, already famous for its anti-tail, now seemed to develop a halo that pulsed in brightness. Every few hours, photometric data from the Las Cumbres Observatory Global Telescope Network revealed spikes of luminosity, rhythmic, almost like breathing. The periodicity matched its rotation period of about 8.3 hours, suggesting that active jets were firing each time certain regions of the nucleus faced sunlight. These outgassing events fed the coma in bursts, throwing plumes of material outward at speeds exceeding 500 meters per second. The most puzzling discovery came from infrared observations using the James Webb Space Telescope. JWST's near-infrared spectrograph, NIR-SPEC, detected strong emissions of atomic nickel and iron vapor, elements that typically sublimate only at extremely high temperatures, far beyond what a comet's surface should reach at that distance from the Sun. It was as if 3I Atlas's outer crust contained metallic compounds that could vaporize under solar radiation, forming a metallic mist within its expanding atmosphere. This metallic vapor gave the coma a distinct bluish-silver sheen in composite imagery, something unseen in ordinary comets. NASA researchers compared the phenomenon to an ionization halo, similar to the plasma environments around certain hyperactive comets like C2012S1, ISON, before its disintegration. In those cases, the metallic vapors interacted with solar ultraviolet light to produce charged particles that fluoresced in specific wavelengths. If the same process was occurring here, 3I Atlas wasn't just a cold rock-venting gas, it was generating an electromagnetic field, however transient, around its nucleus. Ground-based radar from the Arecibo Successor facility in Puerto Rico attempted to measure the coma's particle density. Preliminary results suggested that the dust concentration near the nucleus exceeded 106 particles per cubic meter, decreasing rapidly outward. The innermost region was so dense with vaporized compounds that radio waves scattered significantly, indicating a kind of ionized fog. In practical terms, 3I Atlas was surrounded by a thin, glowing shell of plasma, a cometary atmosphere alive with electric charge. The sheer size of the coma also raised questions about the nucleus itself. If the body was truly less than a kilometer across, how could it sustain such massive outgassing? The European Space Agency's Cometary Physics Division used thermal models from their Rosetta mission to 67P Churyumov-Gerasimenko as a baseline. Those models predicted that an object this small should lose its volatile gases within weeks at such proximity. Yet 3I Atlas kept venting steadily, month after month, as if it had a hidden reservoir, or a way to regulate the loss. One possible explanation lay in its unusual composition of refractory organics. Some laboratory simulations suggest that complex hydrocarbons, when irradiated by cosmic rays over millions of years, can form dense, tar-like crusts that trap gases beneath the surface. When heat finally penetrates that crust, the trapped gases erupt explosively, creating fountains of dust that feed the coma. If 3I Atlas carried billions of years of accumulated crust, then each eruption would expose fresh material, sustaining the coma's brightness over a long period. But not everyone was convinced that this process alone could explain its energy output. The total power emitted by the coma, estimated from its infrared flux, reached nearly 1.2 x 109 watts, equivalent to the energy consumption of a large city. Where was all that heat coming from? Solar radiation alone seemed insufficient. Some suggested that internal radioactive decay or even chemical oxidation might play a role. If 3I Atlas contained peroxides or other reactive materials within its icy matrix, the exothermic reactions could continue long after the initial heating began. The growing coma had another, more ominous implication. Its expansion meant that the nucleus was shedding mass rapidly. By analyzing the dust emission rate, astronomers estimated that the comet could be losing several tons of material every second. At that rate, it might disintegrate completely before reaching perihelion. This process was eerily reminiscent of Comet ISON, which broke apart in 2013 after overloading itself with heat and outgassing pressure near the Sun. And yet, unlike ISON, 3I Atlas showed no visible signs of structural failure. The nucleus remained coherent, its brightness steady. Some speculated that the mysterious forward shield detected earlier might also play a role here, deflecting part of the solar radiation, reducing stress on the core. If so, the object's own behavior was protecting it even as it boiled away. By late October, the coma had reached a record diameter of nearly 400,000 kilometers, glowing faintly even to small backyard telescopes. It became one of the largest transient objects ever observed in our solar system, large enough to eclipse the Sun if placed at the right distance. For astronomers, it was both a marvel and a warning. Something about this object allowed it to endure extremes no comet should survive. It was as if 3I Atlas had evolved for the journey, designed by nature or something else to meet the Sun head-on. As its coma continued to swell, the world's telescopes tracked it relentlessly. Each night brought new data, shifts in brightness, changes in spectrum, fluctuations in its magnetic footprint. And through it all, one thought kept returning. What if this was not the peak of its transformation, but only the beginning? By the time 3I Atlas neared 1 astronomical unit from the Sun, the same distance as Earth, its spectral signature had become one of the most detailed ever recorded for any interstellar body. From dozens of observatories across Earth and in orbit, teams analyzed the light it reflected and emitted. Each wavelength was a clue, a fingerprint of atoms and molecules escaping from its surface. And those fingerprints painted a picture of chemistry unlike anything born under our Sun. Ordinary comets in the solar system are rich in water vapor, carbon monoxide, methanol, and ammonia. Their emissions tell the story of ices formed in the cold outer disk of our early solar nebula. But 3I Atlas, though it looked like a comet, breathed an entirely different air. Spectral lines from its coma showed almost no water, less than 5% of the vapor normally seen at that distance. Instead, carbon dioxide dominated, making up more than 60% of all gaseous output, with smaller but significant amounts of carbon monoxide, hydrogen cyanide, and traces of formaldehyde. These ratios suggested a body that had formed in an environment with limited oxygen and abundant carbon, perhaps near a cool, red dwarf star where chemistry favors the formation of exotic organics rather than simple water, ice. That composition immediately drew the attention of astrochemists at NASA's Goddard Space Flight Center and the Max Planck Institute for Extraterrestrial Physics. They noted that carbon dioxide-rich bodies are rare even within our system. Such an extreme imbalance implies formation temperatures below 30 Kelvin, colder than the regions where our own comets formed. At those temperatures, even nitrogen freezes solid. In such conditions, complex hydrocarbons, the tar-like substances that form when carbon chains interact with ultraviolet light, become stable. 3I Atlas may therefore be made of ancient organic matter that predates our Sun. The discovery of hydrogen cyanide, HCN, added a darker note. On Earth, HCN is highly toxic, capable of halting respiration at the cellular level. In cosmic chemistry, however, it plays a paradoxical role. It is both poison and progenitor. Hydrogen cyanide is one of the key precursors to amino acids and nucleobases, the building blocks of life. Experiments simulating early Earth conditions have shown that when HCN interacts with ultraviolet light and other simple molecules like ammonia, it can spontaneously produce adenine, one of the molecules that forms DNA. Thus, the same compound that could kill any living organism on contact might also have sparked life billions of years ago. 3I Atlas carried this molecule in abundance. Equally fascinating and unsettling were the metallic vapors found in its coma. Infrared spectroscopy from the James Webb Space Telescope and ultraviolet observations from Hubble revealed traces of atomic nickel, NEI, and iron, Fe gas. These metals vaporize only at temperatures exceeding 700 Kelvin, meaning that the surface of 3I Atlas was reaching nearly 430 degrees Celsius, hotter than Mercury's day side. At those temperatures, ordinary cometary material would melt or explode. Yet the object persisted, venting a fine mist of metal atoms into space. This metallic vapor not only altered its color, but also interacted. with sunlight to create faint emission lines that pulsed in sync with the nucleus's rotation, a cosmic heartbeat in iron and nickel light. When scientists modeled the densities of these metals, they realized that the total mass of vaporized nickel was equivalent to over 100 tons released every hour. That figure stunned even seasoned comet researchers. If correct, it implied that the nucleus contained vast veins of metal, possibly alloy-like inclusions formed under enormous pressure. These could have originated near a young star's inner accretion disk before being ejected by gravitational chaos. If so, 3I Atlas was not just a frozen snowball from a distant world. It was a fragment of an ancient, destroyed planet. The mix of gases escaping its surface was not only fascinating but also dangerous. Had such an object ever passed close to Earth, its atmosphere would have been lethally toxic. High concentrations of carbon dioxide would displace breathable air, while hydrogen cyanide and formaldehyde would react with moisture to create corrosive acids. Even the dust would pose hazards. Microscopic grains coated in organic residues and metallic ions could ignite or catalyze reactions when exposed to oxygen. In short, 3I Atlas exhaled the breath of a world utterly alien to ours, one where chemistry itself plays by different rules. The European Space Agency's Rosetta mission data provided a useful comparison. The comet 67P Churyumov-Gerasimenko, visited by Rosetta between 2014 and 2016, released a mix of gases dominated by water, with smaller amounts of carbon dioxide and methane. Its surface was dark, porous, and covered in organic compounds that smelled, as one scientist famously described it, like rotten eggs and almonds. But if 67P were a faint scent, 3I Atlas was a chemical storm. Its emissions were thousands of times richer in carbon monoxide and far more reactive. The ratio of CO to H2O in its coma was the highest ever recorded. That ratio alone suggested a birthplace beyond the known limits of conventional planet formation. Some theorists propose that the body might have formed in a carbon-rich disk around a metal-poor star, possibly one of the old thick disk stars that emerged early in our galaxy's history. In such environments, oxygen would have been scarce, leading to the creation of carbon-heavy compounds rather than silicate minerals. A world born under such conditions could indeed become a toxic comet, rich in cyanides, carbon monoxide, and metals, the chemical fingerprints of an alien system. As the data poured in, laboratory spectroscopists on Earth began replicating the observed emissions using vacuum chambers cooled to cryogenic temperatures. They found that mixtures of carbon dioxide and cyanide could produce the same infrared lines when heated rapidly, confirming that the detections were real. In a way, these experiments allowed scientists to recreate fragments of another world in their labs, small echoes of the chemistry taking place around a comet older than the Sun. Perhaps the most haunting realization was this: the gases now streaming from 3I Atlas had been trapped inside it for billions of years. Every molecule escaping into space was a time capsule, a message from the dawn of the galaxy. When these vapors mixed with sunlight, they formed brief spectral patterns that no human eye had ever seen before, colors and wavelengths that existed nowhere else in the known solar system. For the first time, we were witnessing the literal breath of a world that had never belonged to us. The conclusion, though sobering, was undeniable. If fragments of 3I Atlas ever reached Earth, they would carry materials both fertile and fatal, poisons capable of extinguishing life, but also precursors capable of creating it. In that contradiction lies the paradox of the cosmos itself. The same universe that gives birth to life also holds the power to erase it, molecule by molecule. By late November, 3I Atlas had reached a speed few natural objects ever achieve. It raced inward on its hyperbolic trajectory, descending toward the heart of the solar system like a glowing spear. Every day it moved millions of kilometers closer to the Sun, and every night its brightness grew. To observers on Earth, it now blazed at magnitude 5, faintly visible to the naked eye in dark skies. a rare chance to glimpse an interstellar visitor before it vanished again into eternity. But that visibility came at a cost. As it approached its perihelion, the point of closest passage to the Sun, its angular separation from the solar disk shrank rapidly. By December's first week, 3I Atlas was less than 15 degrees from the Sun in the sky, too close for ground-based telescopes to observe safely. Soon the light of the Sun would drown it out completely. Astronomers called this period the blackout phase, when a comet or asteroid disappears behind the Sun, invisible to optical instruments. For ordinary comets, this is a brief inconvenience. For 3I Atlas, it was a terrifying unknown. The calculations predicted that perihelion would occur on December 17, 2025, at a distance of just 0.39 astronomical units, about 58 million kilometers from the Sun, closer than Mercury's orbit. At that distance, surface temperatures could exceed 800 Kelvin, hot enough to melt iron and boil away most volatiles. No known interstellar object had ever survived such proximity. Some astronomers predicted total disintegration. Others hoped for a miracle, that the mysterious forward shield and dense crust might allow it to endure. To prepare for the blackout, space agencies mobilized a network of solar observatories. The Solar and Heliospheric Observatory, SO, orbiting at the L1 Lagrange point, would have an unobstructed view. So would NASA's Parker Solar Probe and ESA's Solar Orbiter, both operating closer to the Sun than any previous spacecraft. These instruments would be humanity's only eyes during the weeks when ground telescopes went blind. On December 10th, the last clear image from Earth came from the Las Campanas Observatory in Chile. It showed the comet as a brilliant white core surrounded by a sprawling blue-green haze, its coma still enormous, its anti-tail faintly visible ahead of it. Then, as the Sun rose higher each morning, it faded from view, swallowed by daylight. From that point on, the world could only wait. For scientists, this waiting was torture. They knew that as the comet moved behind the Sun, it was entering a zone of extreme heat and radiation. Solar wind density increases dramatically near perihelion, bombarding any object with streams of charged particles traveling hundreds of kilometers per second. Magnetic fields twist violently, and temperatures fluctuate faster than most materials can withstand. For something as volatile as 3I Atlas, it was like flying into a furnace. At SOHO's LASCO C3 coronagraph, engineers fine-tuned the instrument's sensitivity. Its job was to block out the Sun's blinding disk and reveal faint structures in the corona. By December 15th, a tiny luminous point appeared at the edge of the field, the first sight of 3I Atlas entering the Sun's domain. It trailed a faint arc of vapor that flickered as it plunged closer, until its signal grew almost too bright for the sensors to handle. Then within hours, the point began to distort. Some frames showed sudden flares of brightness, possibly outbursts of gas and dust. Others showed dark gaps where the nucleus might have fragmented. No one could tell for sure. The distance was too great, and the glare too fierce. Meanwhile, the Parker Solar Probe, positioned inside Mercury's orbit, recorded unexpected changes in local plasma density. The spacecraft detected a surge in ionized carbon and nickel near its sensors, subtle, but enough to suggest that some material from 3I Atlas had reached the solar wind. Whether this came from vaporized fragments or the intact nucleus, no one could say. But it proved that the object was actively interacting with the Sun's environment. As the probe transmitted its data back to Earth, scientists pieced together the possible scene. 3I Atlas was now within 0.4 astronomical units, moving at over 120 kilometers per second, more than 430,000 kilometers per hour. At that speed, it was completing its perihelion arc in just hours. Any structural weakness, any internal cavity, would be catastrophic. Solar radiation would boil internal gases, and the pressure would explode outward like dynamite. The forward shield that once seemed its protection might now act as a trap, forcing hot gases to build up behind it. For 3 days, signals fluctuated. SOHO's coronagraph caught several intense flashes where the comet should have been, each lasting less than an hour. Some believed these were fragmentation events, pieces breaking off and sublimating instantly. Others thought they were reflections, bursts of light as the forward shield or the debris plume caught sunlight at the perfect angle. Whatever the cause, by December 19th, the light curve suddenly dropped. The object was gone. No trace remained in the instrument's fields of view. It had passed behind the sun, swallowed by glare and plasma storms. In astronomy, such disappearances are normal. But this time, something felt different. 3I Atlas had entered a zone from which many comets never return. Some disintegrate completely, leaving only diffuse dust. Others survive, reappearing on the other side days or weeks later. Which fate awaited this interstellar visitor, no one could say. During the blackout, speculation filled the void. Some scientists believed the object had exploded under thermal stress, scattering its mass into a vast, invisible dust ring orbiting the sun. Others argued that its high density and possible metallic crust might allow it to endure. If so, it might emerge brighter than before, stripped of its outer layers but intact. Online discussions even ventured further, suggesting that the shield could have been designed to survive perihelion intentionally, protecting whatever lay within. On December 23rd, as the sun moved relative to Earth and the line of sight shifted, the blackout period ended. Telescopes from the European Southern Observatory and Pan-STARRS pointed toward the predicted reappearance point, scanning for any sign of the traveler. For hours there was nothing. Then, faintly, a single point of light appeared, dimmer than before but still moving exactly where the orbital models predicted. 3I Atlas had survived. The celebration in observatories around the world was immediate. Against every expectation, the interstellar visitor had passed through the sun's inferno and lived to tell the tale. But its survival raised new questions. What kind of structure, what kind of material could endure such punishment? And if it had changed during that passage, what was it now? The blackout had lasted only a week. But in that short span, the universe had once again reminded us how little we truly understand of what drifts beyond the light. When 3I Atlas emerged from behind the sun, it was no longer the same object that had entered the blackout. Its shape, brightness, and motion told a story of survival, but also of deep transformation. The first post-perihelion images, captured by the Pan-STARRS Observatory in Hawaii on December 23, 2025, showed a nucleus surrounded by chaotic filaments of gas and dust. The once clean, symmetrical coma had fractured into overlapping arcs. The forward antitail had vanished, replaced by a turbulent plume that wrapped around the body like a spiral storm. At first glance, it looked triumphant, a survivor glowing against the dark. But within days, it became clear that something inside the nucleus was tearing itself apart.